Alright, you guys, we're here solving through a couple of the problems I think you might have some questions on from the summer homework packet. I'm going to do a quick, intense look at number 3 and number 4. Those are the two graphical analysis problems. I think those will be the ones that people have the most questions about. The others are pretty straightforward. The Velociraptor problem is kind of a level 100 from our motion topic. Earlier on in the year, first semester, if you took regular physics, number 11 is a force analysis problem. Should be able to do that. And then I think I did get one question about the LOL chart on number 14. That we can talk about in class. I think the word quantitative is throwing you off. All that means is you need to be putting a scale to that. So we can definitely look at that if you want to. So here I am gonna solve through these two problems that require some graphical analysis. The first one about the planet is asking you to make a graph of the data, come up with an equation, and then from that equation determine what the acceleration due to gravity on the planet would be. So we're going to go ahead and make the graph by inserting the chart. You will need to select a scatter plot for this, just like any other graph we do. For some reason it's graphing 2 there, so we'll go ahead and get rid of the mass from the series and add that as an x-axis data range. I'm not sure why it did that. And then if you notice, it's still not really graphing it. For the new thing in Google Sheets is, Google Sheets is to, for some reason, use those numbers as text and almost make a histogram instead of a real scatter plot. So you have to trick it and go back and find this horizontal axis setting under customize, and you will unclick this treat labels as text box so that it will actually graph your points. It's really stupid that it does that now. I'm not a fan. So here is our graph. You can also go ahead and put in a min value of 0 so you can see the whole thing if you would like. But the question was asking for us to insert a trend line. So if you go up to series, you can select a trend line, and we are wanting an equation there. So if I go ahead and see the equation that popped up in the legend or key or whatever you want to call that, we could retype that out. Our y value is force in this case. Our slope is about 7.74. The units for that would be newtons per kilogram. Our x value, or our x variable, is the mass, so we're going to go ahead and call that m. And then it looks like minus 1.57, and that would be unit of newtons. If we are then going to answer the question of what is the gravity force, or sorry, what is the acceleration due to gravity on this planet, we do know that we have some information about force and we have some information about mass, and we're solving for that g. This equation right here is our gravitational force equation. Of course, on Earth, that g is 9.8, but on this planet it is not. That's what we're looking for. So if we were to note that this object, or these objects that were hung from this force sensor, were hung motionless, we would recognize that the force on that motion sensor should equal the gravity force, since the forces must balance. So really this force and this force in the equation are the same. Notice we have the same mass in both cases, or this m factor would be the mass in any case. So really, there's our g value right there. So the acceleration due to gravity on this planet is 7.74. You may be thinking, well, isn't the acceleration measured in meters per second squared? Yes, but remember, newtons per kilogram here is the same as meters per second squared. If you remember, 1 newton equals a kilogram meter per second per second. So if we divide out the kilograms, we get meter per second, which is our gravitational constant, 7.74 on this planet. So it might feel like you're getting pulled down a little bit less there. I'm not sure you would really notice a whole lot. We're going to go over to our next problem, which is the circular motion problem. This problem is stating that you are to graph something that will allow you to calculate that velocity that these things are flying at, or these things, I should say, this mass that they're swinging around in a circle. So it does tell you that there is a constant, and that constant is mass. The mass of this object is 1.5 kilograms. So that's good to know. Anytime you have a problem where they're asking you to construct a graph in order to solve for something like this, what they're really asking you to do is use your knowledge of how the physical relationship that has already been discovered. Use your knowledge of that relationship to come up with something to graph, and figure it out from there. So if we're looking here at the equation that was provided, centripetal force, or the tension force in this case, because you are flinging this mass around on a string, that is equal to the mass of the object times velocity squared divided by the radius of the string. And we're given force radius data. So what we see here is our dependent variable, or the y variable, being force, and the independent variable being radius. That's the r value here. But if you look at this, if we just do a basic XY plot, we're not really going to get the right relationship. We know that the r value is an inverse. So what we probably need to graph is the inverse of the radius, so 1 over radius. I'm going to now change that unit to 1 over meter, and we'll leave the tension force the same. I will just copy that over. And here's the quick trick to do a little math on the spreadsheet. Remember, you just hit the equal sign. In this case, we want it to divide 1 divided by our value from earlier in the chart. And then we will go ahead and drag the little blue box downwards so that we can have it calculate all of those boxes at once for us. Now that we have this created, we can insert the chart. Once again, it's doing that thing. It's kind of annoying. So we will remove that. We will add the x-axis. Hopefully yours doesn't do that to you when you are working on it. And we want to make sure we have a scatter plot. And it's doing that thing again, and it's even putting them backwards this time. That's very interesting. So you'll need to go back here and make sure you unclick this treat labels as text. And it does look pretty linear right after you do that, which means you're going to get a nice slope. If you want to go ahead and make that force 0 so you can see the origin and you can get a better idea of what you're looking at. Remember to insert your trend line. You need to go up to series. You will select linear, and we want an equation there. So we're seeing this equation, 96.5x plus negative 0.163, or in other words, our tension force, which is F, equals 96.5. Our x variable was 1 over radius, so I'll just say divided by r. So the nice thing here is we have a pretty negligible y-intercept. We are asked to solve for the velocity. Unlike the last one, you can't really just pull the slope, because the slope in this graph doesn't necessarily represent all of that. There are a couple other ways to do this where you could have factored some things out. We didn't do that. So what we do know is our slope here should be equal to mv squared, because that was the part of this equation that wasn't represented here in the data. So what we need to do is just do a little bit of math. We know that 96.5 is mv squared. Whoops, where'd I go? mv squared. And we can plug in 1.5 for our m. And we do a little bit of math to solve for v. So if we type it out here, we can figure out pretty quickly what this would be. I haven't actually done it yet. Let's figure it out. 96.5 divided by 1.5. And we will have to take the square root of that. And this is why you don't use iPhone calculators, friends. To the 0.5. It looks like we're looking at about 8 meters per second. And that's what we would get.